Hello everyone. This is the solution video to week 4 assignment of Digital IC Design NPTEL 2024. Question number 1. If the Wn, that is the width of the NMOS in an inverter, is made, well, it's made lesser, right? Because you are multiplying with k where 0 less than k less than 1. That means the NMOS is being made weaker. WP remains unchanged. That means PMOS is the same strength, and so therefore the trip point will increase. Right? In question 2, the gain of the inverter at the trip point is given, and we are asked to use a suitable noise margin approximate model and find the value of the noise margin high. Right? So the formula for that is given, and I've given the working for that here. So question 3 and 4 are eliminated. We've asked NPTEL to make it 0 weightage. Question 5 is about pass transistors, right? So the rule is if an NMOS is trying to pass logic high and it doesn't have any subthreshold leakage, it can only pass logic high up to VDD minus VTH. Whereas PMOS obviously can pass logic high with no issues. So based on that, you can see the two situations and the final voltage that appears. Because VDD minus VTH is still greater than VTHP, the value of VDD minus VTH is passed along without any issues. And finally, you'll have VDD minus VTHN for figure 1 and VDD for figure 2. Here we are allowed to assume subthreshold leakage, and so therefore there's no issue. With enough time, VDD will just get passed. Here are the workings for question 7 to 9. Yeah. First, we work out question 7. Or rather, first, the premise, that is the setup of the question is you have to find out the equivalent resistance of this PMOS device that's charging up a capacitor from 0 to VDD by 0 to VDD. And you're given all these facts about the W by L, KP, the VGS, VTH and all that, right? Question 7 asks you to assume that it is a long channel device, right? And for a long channel device like this, when you're going from 0 to VDD by 2, it is also asking you to take it that it is in saturation region, right? So that is question 7. So the derivation for that is given over here, right? First we have a region assumption, so therefore we can get the current value, which comes out to be 256 microamps. Then the equivalent resistance is it's just, right, you have I flowing like this, and then you have VSD like that. So R, so this is V, this is VDD, right? So R of V is going to be VSD, that is VDD minus V divided by I, right? So that's what I have here, and then you have to integrate R of V from VDD, from 0 to VDD by 2, and then take an average, right? So that's what is happening here. And if you do that and substitute the value for I, you'll get this as the expression in the end, and then you have to substitute the value for VDD and I, and you'll get the answer as around 5.85 kilo ohms. Next, doing the same derivation for velocity saturated for question number 8, and also with channel length modulation for question number 9, right? So So this is just the following derivation, right? R of VdV, VDD minus V divided by minus ID sat on the denominator. So on the denominator, if you notice, it is I is equal to, right, minus ID sat times 1 plus lambda VDS, right? Because why? Because we had defined the positive direction of IS like that, right? But this is the source, right? It's connected to VDD. In a PMOS, the ID is like this. So therefore, I is equal to minus ID. And what is ID? It's ID sat times 1 plus lambda VDS. ID sat is the when V min is equal to VD sat, right? You will get your KP prime WP by LP, V min minus VGS minus VGS minus VTHP minus V min by 2 times V min, right? So that is ID sat. This is ID sat. So yeah, if you do that, you will get a value for ID sat because you know all of these things, right? And yeah, so then taking the derivation forward, 1 by 1 plus lambda x is like 1 minus lambda x for small x, and that will become this, right? This will become this. And then yeah, after that we just substitute that into the equation, and then this is a common variable VDD minus V, so we can just do a change of variable, right? X is equal to VDD minus V, and I just scroll through the remaining integration steps. Right? And yeah, this is the final answer you get for question number 8. This is the equation that you take. For question number 9, this is the equation you take. And doing so, this is the working for question number 8, right? And this is the working for question number 9. So yeah, next question 10, right? We are asked to find the delay at node N2, right? And I've just given the Elmore delay expression for node N2, and you'll just have to substitute the value of k for R and C, and you'll get it as 4k square. Next, if R2 is made 3x, then all that's going to end up affecting is the middle term, and it'll come out to 6k square. So it's 1.5 times is the answer. So a similar reasoning for question number 11, right? The answer, I'll pause the video at this point and you can work it out yourself. The answer is 3 by 4. And for question 12, the answer comes out to be 300 picoseconds, right? It's the Elmore delay expression for N1 to N4. And question 13, it is N1 to N3, which comes out to be 250 picoseconds. Question 14, we have to find N1 to N5 and then N1 to N2 and then subtract, and that is N2 to N5. The answer comes out to be 150 picoseconds. Yeah, and with that we are at the end of the solution video for Digital IC Design NPTEL Week 4 assignment 2024.